So the previous class we talked about the seemingly unrelated regression model, and today we're going to be working on the lab. I'm using my remote connection to my computer in the office, so I hope it doesn't you know the, I hope that the connection doesn't get bad. So to start with, this is the description of the lab that you have access to. I posted it. I sent you by email. I posted in Blackboard too. So basically, in this lab, we're going to learn to estimate systems of equations using both SUR and also simultaneous equation procedures. So I'm going to be dividing the lab in two parts. I usually cover everything, and then both SUR and systems of equation models, and then I do the lab. But this time I decided to start working on the lab right after we talk about the SUR, so we can work on the first part of the lab. And so this first part of the lab covers after what is called section 1, and section 2 will be the part that corresponds to simultaneous equation models. So the example, basically what we're going to be doing is estimating a system of demand equations. It's called the AIDS model, almost ideal demand system. It was developed by Ditton and Milbauer. And there is a simplified version of the model that we're going to be using today, which is called the linear approximate almost ideal demand system. The original AIDS model is a nonlinear model, but we haven't talked about nonlinear models. But the linearized version is very popular. And if you are taking demand analysis class, you can talk more in detail about that. So, in this demand system, of course, we're going to have 3 equations, and I'll explain a little bit, what is that we have in these equations. In these equations, we have the share of demand, we have coefficients, we have the prices, and also we have, these are total real expenditures. Okay, so it's a linear model once we express it in this way. So the share as a function of the prices of the 3 goods in the system, and also total expenditures in all the goods in the system. And of course here, so we have the logs of prices and also the log of total expenditures. So for estimation, I use some data from Ecuador. So this is from the Consumer Expenditure Survey. Now, something that you should know, that if you are using cross-sectional data, as we have here in this example, usually you also have to include in the model socio-demographic characteristics, such as the number of children in the household, education level of the household members, and so on and so forth. But for our purposes in this lab, we only consider prices and expenditures. And we consider a demand system for 3 commodities: meats, dairy products, and pulses. So these are kind of like the sources of protein. Let me show you the data, so that you see how the data looks like in Excel, and you also have access to Excel. So you have the quantities of meats, quantities of dairy products. So this is in pounds. You have income, some socio-demographic characteristics. You have the prices for the 3 goods. You have total expenditures on the 3 goods. This is the total consumption in protein. Okay, and I think that this is expressed like in a 2-week period, and these are already the shares. Okay, but I think that I recalculate them again as part of the program. So basically, if in the survey you have quantities and prices, okay, and expenditure sometimes. All the other variables can be constructed. So let me see how many observations is that we have here available. We have probably a couple of thousands of individuals. Let me see. To show you how many observations we have in total. slow if I go this way. Things are slower since I'm using the remote access. But as you can see, we have several thousands of observations. So we will see exactly what's the number, but I wanted to show you that. That's kind of common in consumer expenditure surveys to have that number of observations. So going back to the system that we want to estimate, so I already described you. Now, to be consistent with demand theory, the parameters in this demand system need to satisfy certain restrictions. So the first one is the homogeneity restriction. And, just a reminder for those that have studied economics, basically the homogeneity restriction says that if all prices are increased by the same, if all prices and income are increased by the same proportion, the demand will not change. Sometimes that's called money illusion too. The second one is the symmetry restriction. Basically, some of the coefficients are related to each other, and I'll show you that in a second. And also we have the adding up restriction. And basically, the adding up restriction, the sum of the shares has to be equal to 1. And this restriction is satisfied if these conditions where the coefficients are also satisfied. And I have prepared a handout for you where I show you exactly, what does these restrictions look like in the context of our example. So, these are the three goods. So, these are the three equations for the three goods. So we have alphas. The alphas are the intercepts. The gammas are the price coefficients. So this is for the first equation, the first price, the first equation, the second price, the third equation, the third price, and the betas are the coefficients for total income, and so on and so forth. So this is the way that's written the homogeneity restriction in this context. And basically the homogeneity restriction tells us that within each equation, that's why we have J fixed, the sum of the price coefficients is equal to 0. So this coefficient plus the second coefficient and the third coefficient of the third equation is equal to 0. And the same thing for the sum of the coefficients of the price coefficients of the second equation. And the same for the sum of the price coefficients for the third equation. The symmetry restriction has to do on what are the effects of prices. So, for example, like the effect of price 2 in the equation 1 has to be on the share of product 1 has to be equal to the coefficient of the price of the first good on the second equation. Okay, so that's kind of like the symmetry restriction, what that implies. And we have another restrictions for 1, 3 and 3, 1. So the effect of price 3 on the first equation has to be equal to the effect of price 1 on the third equation. 1, 2, 1, 3. Then we'll have the same thing for 2, 3 and 3, 2. And these are the three symmetry restrictions that we have. The adding up restriction, the sum of the three intercepts has to be equal to 1. The sum of the beta i's, the sum of the three income coefficients have to be equal to 0. And for the adding up restriction, this kind of looks similar to the homogeneity, but it's different because now what stay fixed, so let me see, is J, and what changes is the coefficient K. So basically what that is telling us that what we're adding up here are these three coefficients. And let me see if I can show you. You have these three coefficients, the one that have to be added to 0 for that adding up restriction, these three coefficients, and that kind of makes sense because remember the restriction is that the sum of the three shares have to be equal to 1. So the adding up restriction involves the coefficients of the three equations. Okay, and that's kind of what we have in here, but it's expressed in a line. Okay, so that's more or less what we have. regarding our model so far. So that's kind of what we want to estimate. That's kind of like the background, kind of a little bit fast. So let me go again to the lab. So that's what we have. So, for SAS, as usual, import and manipulate the data, and I'm also provide you the program. So I'm gonna do exactly the same thing that you're supposed to be doing. You have to go to SAS, copy paste the file. I'm gonna give it a name, and I'm gonna save it in a file where I have all the labs. So I'm gonna call it lab 3. So this is the class. Okay. So we have to import it. Of course, I need to select where I have it saved the protein file. I'm gonna close it. I'm gonna close it here. And I'm gonna go and look for the place where this is located. Let me see, copy as path here, and this will allow me to change this. And I guess it's sheet 3. Let me double check. Well, it should work. So let me see. And I'm also gonna be calculating the means to see if things work out well. Okay, so it's taking some time since I guess it imported it. It has 2000 observations and 22 variables. I also calculated the means. So I have all the data, but just for us to practice what I did here, and some things change, give me in different lines, but I usually like to have one line for each operation. So I'm changing this thing. So basically what I'm doing here is I'm calculating expenditures for meats. This is the price times the quantity for the 3 products. Y prod is total expenditures in meats, and then I calculate the shares. Of course, the shares is expenditures in meats divided by the total expenditures in the proteins. And I can calculate the shares for the 3 types of meats that I have. Calculate the log of the prices. Okay, and I call LNP meats, dairy, and pulses. So this LNP star, this is some sort of a price index. So this is called the Stone Price Index. And the Stone Price Index is the product of the shares times the natural log of the prices. Let me make some note here. Let me see if I'm going to be able to write this here. Since I'm using my desktop, maybe I should try to make a note here. So this is what I'm using, and I'm using my finger. Stone Price Index. And this is basically the sum of the shares times the natural log of the prices. So it's just like a price index, In the US we have a price index, and this is a specific type of price index. So that's kind of what I'm calculating in that line. Let me go back to the program. So that's I'm calculating here. I have the log of total expenditures. So basically what we have here is real. Y is real expenditure. So what I'm doing, I have the log of total proteins minus the log of the price index. Okay, so and this is kind of, so this is the log of real total expenditures. Again, I'm gonna go back to give you a little bit more background, so what we have there, I'm calling it the log of real total expenditures. I'm saying that's equal to the log of total expenditures divided by P. But since, let me change this option. But since we have logs, we can write it as the log of x minus the log of p. So it's the log of total expenditures minus, our stone price index, which is expressed in log form. So that's kind of what we have there in that part of the equation. Okay. And then I also have the natural log of income, and this income plus 1, since there are some households whose income is 0. And I'm not going to be using that for now. Okay, we will use that later on. So the first part, as I was telling you, we're going to ignore any sort of endogeneity. So this is the SUR model. Remember, one of the assumptions in the SUR model are exogeneity or no endogeneity. So, we start as usual calculating the means, and actually we will compare to see if this is similar. I should write the program, and the shares of the means, for example, 0.65 is very similar to what I had there. I had pre-calculated that, I did it again. Okay, so the same values, just to show you how you go about doing things. Okay, so now let's go with the lab. So remember, we had 3 equations. So this is a demand system. So one way to go about doing it is we could estimate each equation separately. So we have the share for meats as a function of the price of meats, price of dairy, price of pulses, and real total expenditures. We can write that. I mean, that's nothing new. I think that's the first question that I have in the lab. This thing kind of looks a bit strange, but that's kind of the way it is. So there seems to be some sort of heteroscedasticity, but for now we're going to ignore that. Later on we will talk about some more. Normality seems to be kind of violated, but let's ignore that for now. So everything looks good. I mean, 2 prices are significant, one's not significant, and total real expenditures is significant. R squared is very low. Cross-sectional data, that happens. Okay, so again, going back to the lab, if we believe that it's the model, basically, what I'm asking you here is use progreg to estimate the 3 equations separately and report the estimation result. So something that I would recommend that you do here is, and let me see if I better open it. I'm going to be opening this file here in this computer. I think that's probably better, so I can make some notes. Let me see the lab. I use PF annotator. I have added PF annotator to my computer at home. So use progreg to estimate the 3 equations in the system separately, report the estimation result. So, make sure that you do like a table, I would say. So, use a table here. You can use a table where you have here, you can have here the variables. This is being slow, so you can have here the variables. And then, you can have the first share, the second share, the third share, and then here you can have, of course, you're going to have the intercept, and then you can have the 3 prices, so on and so forth, up to the real expenditures. Okay, so that's the way that you can report, like a little table there. And here, of course, you have to estimate your betas and the standard error for each one so that you can compare. Okay, so add like a little table like this one, I will say. In the second step again, use proc model, but instead of originally I would like you to use OLS. And of course, again, like a little table like this one, and the results should be the same. I mean, that using proc model OLS is the same as using progreg for a simple linear equation. So also here, make sure that you include a table. And when I say compare the results, compare them. So discuss, add a little bit of a discussion. Every time that I say compare, add some discussion there. And then use proc model and SUR to estimate the system. Actually, let's do that kind of together. So hopefully you are following it with me. So proc model, okay, well, so here again I copy paste from, a reminder, I think that we already used before proc model. So the data, the endogenous variables in this context are just the dependent variables. The independent variables are three explanatory variables. So remember, when we do proc model, we have to write the equations with the coefficients. So that's what I did. I have meets, dairy, pulses. So meets is 1, dairy 2, pulses 3. So I follow the same order. The A's are the intercepts. The G's I use instead of the gammas. So 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. And the B's are the, I'm using B for total income. And I'm estimating the three equations using SUR. Okay, so let's do that. Oh, there's a problem. I don't know what happened. I did again. I have again an error. Yes, it seems that it's working, but did I get the results? Not yet. I don't know what happened. That's strange. Let me run it again. Oh. I'm not getting any message. And I'm not getting any output either. Let me run everything to see what's going on here. I thought I had created everything. Let me import. Let me see what's going on. Okay, I think I finally ran. I think that probably was taking some time to run it for some reason. Okay, so again, initially I told you to use OLS. Okay, so let's use OLS first. Three equations separately. And now it's working. Okay, so there's convergence. Proc model uses nonlinear procedures. So that's what it took about convergence. Let me see. So yeah, and I have the same coefficients for the first equations. 0.64, 0.57 minus 0.32, which I think that it was. Oh, okay. Well, this is not yet. 0.64, 0.57. Okay, so it's the same thing. So we have the same results, and here you can see that we get an R square for each of the equations separately, but when it gives us the coefficients, it gives us all of the coefficients at the same time. There's no problem here, so that's kind of more or less. Of course, if we want to use SUR, it's very easy. You just type SUR and run it. Okay. Let's see what we get. So this is we're supposedly using SUR. Remember, I mean, we talked about that estimation procedure in class. Oh, and now we get this issue here, and then have warning. The covariance across equations is singular. The generalized inverse was computed. Blah blah blah, so on and so forth. If you go to the log, we get kind of the same thing. Well, the problem, and this is an issue with the systems of demand equations. So remember, since the shares add up to 1, when we try to estimate the system, we have a singularity problem, and it has to do to the fact that the shares add up to 1. So in order for us to be able to estimate this type of demand system, using SUR, again, it has to do with the fact that we have a demand system where the sum of the shares is equal to 1. So there's a problem with error terms. So we have a singularity problem. We need to drop one of the equations. Okay, and I don't know if I mentioned that here in the lab. Let me go and open it. So compare using prog model and SUR. So that's what I was telling you. We use OLS. So here you have to try. When I say check the log window, and then what I'm asking about the problem when estimated the model with 3 equations, and this is what's called a singularity problem. Okay, so we need to drop 1 to be able to estimate the system without any problems. And that's kind of what I say. Next, drop one of the equation and estimate a 2-equation system using prog modeling SUR. And let's check at the log window, and so there is some evidence of we could have conducted a test, but graphically there is a some evidence of heteroscedasticity. Well, let's go step by step, since I'm asking you to use that if possible. So let me go to the program. So we're here, I was telling you that, so you can drop the last equation. We don't need to estimate this one. Let me see if we request white test before we do anything else. So let's do that. Oh, and again, I got a problem. What happened? I made an error. Well, okay, so here I'm supposed to be estimating only the area. Okay, and what I did is, I said drop one of the equations. It's just I can take that one out, and let's see what happens here. Okay, see, so white tests evidence of heteroscedasticity in each equation. Heteroscedasticity test is going to be white test for each equation separately. So we have some evidence of heteroscedasticity. It seems that we have a problem. Let me see what happened. Oh, criteria met, so everything is good. I mean, it says that it converged, so there's no problem there. Oh, the thing is, okay, I'm getting this warning because I have it here as endogenous pulses, but I never use it. But that should not be a problem. I think we could leave it there without any problem. So, and we have, our coefficients are, SUR coefficients estimated in this way. So let me go back. Okay, so where are we in terms of the lab? Let me see. Okay, so we estimated, we found evidence of heteroscedasticity. Well, let's see if it's possible to use HCCME equal to 3, which is the variant, the heteroscedastic consistent covariance matrix. So now we already estimated that. HCCME equal to 3. Let's see if it's possible. We will see. Okay, so the system estimated. It used the HCC method as we would like. Okay, so everything looks good. So it was possible. So we corrected for heteroscedasticity. Okay, so the next step is to see if we can test those restrictions. Okay, since we had to drop one of the questions, we can only test for 2 of the questions. So this is, and the test can be done separately or together. We're going to be doing the homogeneity test and the symmetry test. Some of you might be wondering, okay, so what about the adding up restriction test? Well, it happens that since you drop one of the questions, in a way you are kind of imposing that restriction. By dropping the question, you are imposing that adding up restriction. Okay, basically the model forces you to impose it in a way by doing that. Okay, so let's do that. Again, before we even look at the heteroscedasticity issue, let's just use SUR to see what happens. So we're going to be testing. So the null hypothesis is that the restrictions are satisfied, and the alternative is that they are not satisfied. So we have our results, and here we have the tests. So remember, the null hypothesis is that the restrictions are satisfied. So for the first one, we reject the null hypothesis that the homogeneity restriction is satisfied. So we reject that one, and this one we fail to reject the validity of the symmetry restriction. Yeah, so I'm going to summarize that so that you have a guide for the discussion. Let me see. There's a restriction. So we have the null hypothesis is that homogeneity is satisfied. And the alternative is, of course, not the null hypothesis. So that's the first one. And, we're testing them separately. So the other restriction is that symmetry. And I'm gonna is satisfied. And the alternative is not the null. Okay, so from what we saw, we reject the homogeneity restriction, but we fail to reject the symmetry restriction. Now, I know that some of you might say, well, that's bad, that means that economic theory is not good. Well, it's possible. Remember, this is just one data set. I mean, we did not include some other socio-demographic characteristics. So I would say don't think too much about it. Now, there's a lot of times where actually economic theories are satisfied. And that's kind of problematic. And sometimes that has led to the development of new theories. And that's the way that it should be. Okay, so, there are different objectives of testing. And this is the way to go about doing it. I mean, again, if you take like an advanced demand theory class, you have some more discussions about these things. But that's the way in which you can test those restrictions. Okay, so let's see if it's possible to use HCCM3 for our purposes. Let's see. So we want to test GCME equal to 3. Okay. See what we get. Okay, so we get the different tests. Everything seems to be fine. Let me see the log. Everything looks good. So actually, see, we were able to, to do the test accounting for heteroscedasticity. So that's pretty good. Okay. Let me see. So everything so far so good. I hope. Going through too many computers. It's kind of confusing. And then, so you see two things going on here. See, here we were testing the theory. Okay, so you can test the theory to see if they are valid or not. In the next step, what we're doing is that we're estimating the system of equations, but what we're doing here is imposing the restrictions. Okay. Now, you might be wondering, okay, so you are telling us that you test, but if we reject those hypotheses, what do we gain by estimating a demand system imposing something that we find that, we find that there is statistical evidence that those restrictions are not satisfied, where, we need to impose the restrictions if we want to do some further analysis, especially, if we're interested in doing welfare analysis. And this is kind of where things get tricky, because, one of the uses of demand systems is actually welfare analysis. So in welfare analysis of policies or shocks. So, for example, if there is, some sort of economic shock, like a sudden increase in the prices of just for meats, you want to see what's going to be the welfare effect of the increase of the pricing of meats on the population. Okay? Well, you estimate your demand system, and what you do is using your coefficients of demand system, you can go back. So this is kind of the in theory. So you have your system. Since that is derived from economic theory, you can go back to your expenditure function. Or you can go back to your indirect utility function, depending on the demand system that you have. And once you have that expenditure function or that indirect utility function, you can do welfare analysis. But the tricky thing here is that in order for you to go back from the system to the expenditure function or the indirect utility function, the restrictions, the demand restrictions need to be satisfied. Okay? Otherwise, you cannot go back. So again, for welfare analysis, kind of like an intuitive way to think about it, if we want to do welfare analysis, we need to believe that these people behaves according to our model. If not, then we cannot do welfare analysis. Okay, so that's kind of what, more or less, and again, here I'm waving my hands, that's what you need, these demand restrictions to be satisfied. So you impose them during estimation. So in practice, how do we go about doing that? Well, actually, it's pretty easy. We just write restrict and write, all the things that we want. So we want the system to be homogeneous, and we also homogeneous of degree 0, and we also want the symmetry restriction to be satisfied. I'm going to rewrite here the model. Okay, so, and again here, first let's use without HCCME to see what happens. Okay, and then, instead of having test, we just write restrict and run the model. Yeah, so let's wait to see what happens. Well, so the restrictions actually get tested. And actually, in this case, they are all, rejected. And let me see. So the restriction of homogeneity. Let's look at the symmetry restriction. We say that 1, 2 is restricted to be equal to exactly 2, 1. That's easier to check. So you see you have minus 0.31 and J1, 2 is minus 0.31 and J2, 1 is also minus 0.031. Okay, so that's satisfied. If you go and check the sum of these three coefficients approximately, you see G11, G12, and G13 is approximately 0. And the same thing with 21, 22, and 23. The sum of these three is approximately, it actually has to be equal to 0. I'm saying approximately if you look just, check without a calculator, just using your eyes, you see that the sum of those three coefficients is equal to 0. Okay, so now let's impose HCCME equal to 3. Okay, so sometimes you have to be careful, sometimes it works, sometimes it doesn't work. So this is a restricted model. Okay, so let's see what happens. And here we had a problem. Okay, so you see, and that's a problem sometimes with using HCCME3, non-positive definite covariance metrics. Some standard errors are set missing. So you see for the restricted model, here this is a case where we cannot use the heteroscedastic consistent covariance metric. So very likely we'll have to use bootstrapping, to be able to account for heteroscedasticity. Okay, and that's kind of what I've been trying to show you. Look, with and without heteroscedasticity. So that would be a limitation, and again, we will have to account for that limitation. Again, or the other option, of course, would be also to estimate like a generalized regression model. Weighted least squares, but that's more complicated. So probably the easier way to go about doing it would be just doing bootstrapping procedures. And we're almost done with the lab. Let me see. I think there's probably one more part. Well, with this part of the lab. So recover the parameters of the third equation using the demand restrictions. So remember that we had to drop one of the equations. So how do we go about estimating the coefficients? Well, some of you might be tempted to estimate the model dropping the other equation to recover the coefficients of the equation that you have not estimated. But another way to do it will be to use these restrictions. Okay, so you see, for example, we need alpha 3. So from this equation, we know that alpha 3 is going to be equal to 1 minus alpha 2 minus alpha 1. Beta 3, same thing, it's going to be equal to 2 minus beta 1 minus beta 2. And we can do the same thing for 3, 1, 3, 2, and 3, 3. We can solve for them, and that's the way that we can recover the coefficients of that equation. Now, so the other alternative, for example, I'm supposed to be using these ones. So here, this was an error. Let me go back a little bit. I deleted too much. Okay, so so here you are supposed to solve from this one. Is that you are supposed to solve for alpha 3, 1 Okay, it's going to be equal to minus alpha 1, 1. So alpha 3, 1 is going to be equal to minus alpha 1, 1 minus alpha 2, 1, which you already have estimated. Okay, and the same thing for alpha 3, 2, alpha 3, 3. So remember, what we're trying to do is we're trying to recover the coefficients of this last equation. Okay? Now, there are other ways also in which to recover the coefficients. So, for example, the alpha 3, 1 can be recovered using the homogeneity restriction, since we already have the gamma 1, 3. So we have that one. For the 3, 2, the same thing. Okay? You see? And then for the alpha 3, 3, actually we could either use the homogeneity restriction, or we could use our adding up restriction involving the gammas of the third price. Okay, so that's the way that you're supposed to be recovering those coefficients. So I think that this week, I don't want you to I mean, you should be working in this part of the lab. I mean, I'll let you know when the entire lab is due, but I think that you can start working with this part of the lab, and that way you can practice the theory of the seemingly unrelated regression.